thanks a lot for this great introduction. Actually, I'm very, very happy to be here today and to tell you about two of my most favorite technologies. So one of them, namely, is quantum mechanics. That's something that I studied intensively over almost a decade. And the other one is machine learning, something that I fell in love with after leaving academia and working as a data scientist. And yeah, so I'm very, very thrilled to talk about these two topics today. And actually, when it comes to machine learning, I was actually so enthusiastic and thrilled by the application of machine learning to real use cases and problems that I started founding my own company, which was focused on machine learning and computer vision. And after having successfully sold my company, we're actually about to start a new venture here, which is exactly focusing on this thrilling intersection between quantum computing and machine learning. So for all of you here, or at least some of you, probably quantum computing is something rather new. So to give you a little bit of a guideline through my talk, I will start telling you a little bit briefly about the fundamentals of quantum computing, tell you what it makes this kind of technology actually so great and where the advantages of this kind of new type of computing are, and finally give you some examples how to apply that to machine learning. So let's get started. And maybe you wonder, why the heck should I worry about quantum computing in the first place? Yeah, maybe you just successfully installed your huge cloud cluster or running in a high-performance computing supercomputer somewhere and wondering, well, why the heck should I bother with quantum computing? And the answer to that is pretty simple, because all of us know that in the end, computing is based on hardware. So all the logics, all the magic is actually encoded somewhere in hardware, that the hardware is enabling us to store information, to process information. But on the other hand, it's also limiting what we can actually do, what we can compute, and how efficiently we can do that. And this question is not new. As you see here, for example, there was a now famous conference at the MIT in 1981, where leading scientists of their fields at the time, coming from physics, coming from computer science, we're pretty much discussing this topic as well, and we're searching for new ways to overcome this kind of limitations that hardware actually pose to computing. Because there's a lot of very interesting problems that are really hard to calculate on hardware, and also, you might be aware of that, I mean, we're running into some kind of bottleneck as well, so we're stuck with miniaturization and can't make it any more smaller, so we're really crashing into the physical boundaries. So they were really discussing here if we can use quantum mechanics to overcome these challenges. And one physicist was there who I pretty much idolized, so it was a big role model and yeah, a really famous physicist, maybe you've heard of him. It's called Richard Feynman. He was there as well. And he pointed out at some point where he was just maybe losing the nerves in the discussion or something, because bear with the language, but he pointed out a very important point. Nature is quantum, goddammit. Sorry for that. But so if we want to simulate the nature, we need a quantum computer. It's not about should we do it or not. It's pretty much a necessity if we will ever have the chance to understand reality and the nature and to model and simulate it. So that was pretty much the starting point of quantum computing. So the term quantum computer was coined by Richard Feynman then. And yeah, today I'm standing here roughly, 30 years later, and you might ask, why am I telling you that now? So, well, point is, the comment by Feynman pretty much steered also interest in the scientific community, and they went back into the labs and trying to figure out how to build a quantum computer, how to control it, and how to actually make it compute things. And guess what? They were pretty good at that. And at some point, they were actually so good that they managed to build hardware that, came out from the labs and went into the industry. So what we're seeing right now, over the last 20 years, is that quantum computing has actually leaped into the industry, and all the major players out there, all the hardware vendors, are pretty much focused on this field and trying to develop a real working quantum computer. And as you can see here, they made some progress, which is quite okay. Starting with just very small systems. So we see 2 qubits here. I will get back and tell you a little bit later what qubits actually are. It just is the basic unit that you need to run a quantum computer. And we see quite impressively that systems became larger and larger. And finally, especially in the last 2 years, you could say so, there were some giant, rather impressive leaps where we have really grown up the size of the quantum devices to a size where we can really start tackling real-world problems with it. So where we can really do something with it. And it's not just the hardware vendors that are really trying to build here the universal quantum computer. Having reached this point, that also steered the interest of the industry. So what we see right now is there's a lot of huge companies out there trying to harness the power of these devices to actually calculate for the first time and solve for the first time the really hard business problems. For example, to point out some, I mean, we're in Munich, so I pretty much focused on these 3 here. So it's BMW and Daimler, for example, use these kind of devices to research material in order to build new batteries, which they pretty much need in the upcoming age of electronic cars. And other very impressive case was done by the Volkswagen group, where they used a quantum computer to simulate the traffic flow in the city of Shanghai and optimize it. That was quite successful. And also, last but not least, for example, here the chemical company BASF is using quantum computers to research new chemical materials or to optimize their reaction processes. And as you see, there's a whole bunch more huge companies, well-known companies, working with this kind of technology to solve their hard problems. Okay, try that. So, what's the key message here? Well, quantum computing is there, it's out there, and you can use it. I hope you still understand me. No, it's okay. So, yeah, it's there, we can use it, but what's actually magic? I mean, we've seen, 128 qubits was the last number there, so you might still think that's rather small, so how could they actually use that to really solve hardware problems? And the magic lies with what is actually a quantum computer. So now I would like to briefly introduce you why this is actually so powerful. Starting here is pretty much this basic logic unit that is used in computation. That's the qubit that was just seen on the slides before. So qubit basically stands for quantum bit, not so creative, I would say. And it's usually depicted in this kind of so-called block sphere. It's not so important, but I will just guide you through it. Similar to the classical bit, which is still basic logic unit of the hardware we're using on an everyday basis, so to say. The block sphere or the qubit has the 0 state, which is depicted up here, and 1 state. So it's just logical yes or no, 0 or 1. But as you can see in this picture as well, the general state of such a qubit, of such a logic unit, denoted here by this vector psi, is or can be somewhere between 0 and 1. In fact, it can be infinitely many possible states between 0 and 1. And that's due to a quantum mechanical effect that we call superposition. So basically, this state is a superposition, mathematically speaking, it's a linear combination between these 2 states. So it's mixing these states. You could say at some point it's 0 and 1 at the same time at some kind of mixture. So it could be 20% 0, 80% 1, or the other way around. And yeah, that's pretty much the most interesting point, and something that really we will see in the next slides boosts this kind of computation power to a completely new level. At that point, however, you might ask, stop, if that's a logical unit, usually this kind of state doesn't make sense at all, right? I mean, if I pose you a logical statement, then the answer to the statement is either yes or no. So either it's true or it's false, but it's never 20% true and 80% false or something like that. And that's absolutely true, but it's not actually contradicting the kind of logic here, because the point is that this kind of superposition state for a qubit is just there as long as I'm not disturbing it. And in the end, if I want to read out this qubit, I disturb it. So in the end, what I need to do at some point is I need to measure this state. And when I measure this state, then it will collapse to the logical units that we're used to. So it will pop out an answer that's either yes or no, that's either true or false. However, this will occur with a probability. So that's the probabilistic unit that we have here. And these probabilities are actually related to the coefficients that we see here in the mixture states. And that's pretty much a lot of the magic of quantum computer, this kind of superposition. And if you find that weird, you're in good company. As far as I know, there's not a single physicist out there that really understand that it's what that actually means. But over 100 years, nature has told us over and over again that's exactly the way to describe it. And that's absolutely true, what we're seeing here. So, to bring it down and summarize it a little bit more, let us compare that to the classical bit, to a classical computer. So the usual logic unit on a classical computer is bit. It's either 0 or 1. As I mentioned, the qubit, on the other hand, could be 0 and 1 at the same time. And that comes as a price, as we've seen, namely that the quantum computer is working on a probabilistic logic, whereas the classical computer is always deterministic at any point in time. Okay, let's pump that a little bit up. I'm always doing here a single qubit or a single bit comparison. Usually if we want to encode information or process it, we're dealing with strings of these kind of logical units. So just giving you a brief example, what does it look like in these two architectures? Having 2 bits in a classical computer would result in 4 states. So there's 4 combinations that can pop out or that I can use to or encode in 2 bits. And these are pretty much, at any point in time, with 2 bits I can just realize one of these 4 states, right? And on the other hand, as we've seen, in quantum mechanics there is this kind of superposition, and this superposition is not just on a single qubit level, but if I take 2 qubits and couple them, I will have a superposition of these states as well, which pretty much results in the point that we see that the final state of the whole system of these 2 qubits, it's still one single state. And this single state describes all the possible mixtures of the 4 basic states that we're used to in a classical computer. And this is at any point in time as well. So when it comes to processing information now, so that's the storing side. And if we want to process them, usually in the classical computer, we have to go through all these kind of states one at a time. So I start with one state here, I process it, I go to the next one, I process it, and do that for all the states that I have. On the quantum side, however, I just have one state. So I pretty much can process all the information stored in the state at the same time. So it's simultaneous. And that gives us a huge speed up in computation. How does it work out? I mean, maybe for these 2 states or for these 2 bits, it's not so impressive, but let me give you another example which might make more sense and maybe illustrate it a little bit better. So take that formula here, for example. Looks pretty simple, but in fact it's well kind of on the core of all of the encryption that we're using for our let's say if you make online banking or if you buy something at Amazon, in order to have this transaction secured, you're relying on some kind of encryption algorithms. And all these encryption algorithms are pretty much based as a mathematical problem, which is hard to calculate, but easy to validate. So what does it mean? If I give you a large number n over here and ask you to give me the primes p and q that actually constitute this number, then that is a really, really hard problem to solve on a classical computer, given that n might be a rather huge number. And it will take really long, even on the highest level of supercomputer, to actually calculate that if n is just large enough. On the other hand, if I give you p and q and ask you, is that the answer to your question, then you just need to multiply that. You just need to multiply, and you can easily verify if this is a solution to my question or not. And that's pretty much the core of all encryption algorithms. And what does it actually mean? If we look at the classical, at the runtime, if we want to crack a huge, large number m on my laptop, for example, then it might turn out that I have to calculate for, well, long enough that the universe probably crumbles down again. So it's not really feasible from a practical point to actually crack that. That's pretty much the reason why all our transactions are safe, and can encrypt your data and be relatively sure that nobody will have the possibility to crack it. On the other hand, for quantum computing, there's a well-known, very efficient algorithm out there called the Shor's algorithm, which actually can save or solve this kind of problem, in just a glimpse, so to say. It just needs seconds. So, having this kind of computing power pretty much means that all our encryption algorithms are, well, corrupt. You can all crack them in the end. And that's pretty much a direct result from being able to calculate all the possible combinations of p and q simultaneously. Whereas in the classical computer, I have to brute force run through all the possible combinations, which takes just ages, right? And if that's not impressive, that's pretty impressive, I would say. That's the exponential speedup. That's something that really steered all this field and all the effort that's put in to build this kind of computers. Basically, they are exponentially faster than classical machines and can solve really, really hard problems that you're not able to solve on any classical machine. Not now and not in the future. Doesn't matter if it's the biggest supercomputer ever, but still it would be outperformed by a quantum computer with just a couple of maybe some dozens or some hundreds of qubits. And it's not just the computing power that's exponentially faster, but it also scales quite impressive. Namely, if I want to double the computing power of a quantum chip, I just need to add one single qubit. That completely doubles the processing power. Whereas if I take a supercluster or a supercomputer, I need to double all the resources. So I need to double all the number of all the microchips that I've put in there. So that's also something that will help us be more, or take less resources in order to get an exponentially faster calculation power. So that is pretty much one of the main advantages of quantum computing. But there's even more. For example, we had this computational speedup due to the simultaneously processing of all the states. But due to the properties of quantum mechanics, which for example is a linear theory that is happening in infinitely dimensional vector spaces, it's pretty efficient in linear algebra. So it has been shown that there's exponential speedup for multiplying matrices, for doing Fourier transformations, or solving linear algebra systems, basically. Another nice property of these quantum systems or quantum states is that they naturally evolve into optimized states. So they are also pretty nice and very effective optimization solvers. And on top of that, as mentioned before, this huge scalability of these devices is actually helping us to reduce computing costs. And last but not least, due to the probability or probabilistic properties of quantum mechanics, it's also very effective at sampling probability distributions. So, for all the machine learning experts here, you might already see that there is a large benefit, especially in the field of machine learning, because all the machine learning algorithms that we're using today are pretty much linear, or working with linear algebra. They're optimizations, solvers in the end, and they're also, when it comes to statistically or probabilistic models, very heavily depending on sampling. So that's pretty much what puts AI on steroids. That's the point that I wanted to make. So it's speed up the model training. It's very efficient in processing large data sets, even complex data sets with highly correlated data. We have more complex model architectures available because we don't need to make so much trade-off between solving a problem and spending resources on it. And due to the properties of quantum mechanics, we can also handle non-classical data, so generate them, which is not possible on a classical computer. So how do we get hands-on? And I think I need a little speed up here. So I just wanted to point out quantum mechanics in combining with NL, machine learning in practice. There are different perspectives on that topic. You could use machine learning to control quantum systems, which is still a challenge in experiments. You can also be inspired from the quantum computing to actually design and improve classical machine learning algorithms, or you can really do quantum machine learning in the sense that you're implementing your classical machine learning algorithms on a quantum device, and that's one of the points that I hopefully will manage to talk about in the next 5 minutes. So let's have a look at what is actually done there already. So there's been a lot of progress in this field already, and many classical machine learning algorithms have already been implemented on quantum devices. So we see here from the supervised side, as well as the unsupervised side, quite an impressive list of machine learning algorithms. There's also been reinforcement learning, although that's quite new in the field. We'll pretty much just focus on this, on the supervised and unsupervised cases. I mean, you might say, okay, great, it's all out there, so just I'll take my deep neural net, put it there, and harness all the power, all the processing power. Turns out, well, you would say it's a great idea, but it turns out with the devices that we have available right now, it's more efficient to think of them in a different way. It's more like thinking of these quantum computers as special purpose devices that we might use to solve the hardest problems in our machine learning algorithms. And here is how that might work. We've just seen something similar, GANs, but that's the variational autoencoder. It's a little bit, or it's a well-known neural network approach where you have pretty much a encoder side where your input is encoded, it's projected in some low-dimensional so-called latent space, and afterwards it's decoded again to give an output in the data space. And if you train such a network in the sense that you would demand that the input equals the output, you basically encode all the statistic about your data sets within the latent space. And the latent space is, so to say, it's a low-dimensional space which represents the high statistics of your data set. And the problem here is that usually sampling this data set is a hard task for classical systems. So that's where you make errors that might influence the output of your network and the security. But as mentioned before, the sampling can be done efficiently via quantum devices. So what is done excessively is using hybrid architectures, in the sense that you still have all the main components of the network is in a classical computer, and the latent space you will encode in a quantum chip. And what you do is you run all this updating cycle many times to train the network. So you're sampling from the quantum computer, put it in your classical computer, optimize the parameter set respective to some objective function, and put the updated parameters back into your device. And you do that until your objective is reached and optimized. And with this, we have then encoded all the probability distribution in the quantum computer and can use that as a generative model. We've just heard about these kind of models in the previous talk. So that's general structure where we just skip, so to say, the encoding side. We take just the latent space, we sample from it, run it somehow through our function or a neural net or whatever, and get data back. And that is what it can really be done efficiently on a quantum computer. And it's not just some hypothetical, well, toy model, but it really has real-world applications, as for example in simulating chemistry or in finding new drugs, and also, as we've seen before in the talk from Florian Roman, to generate new images or to synthesize speech. And that's for the generative models, but there's obviously much more that we can do with quantum machine learning, and so I just want to point out that there is a whole bunch of use cases across all industries, and just to pick out a few of them. So, for example, in automotive, you can make traffic simulation like Volkswagen did, or try to help autonomous driving while due to the processing of large amounts of data. You can heavily use that in material science to find new battery cells, new materials for solar cells. You can also make polymer folding or optimization. You can use it in logistics, in aerospace, and also in all these other verticals as well, because optimization problems you will encounter everywhere, and very often they are pretty hard and complicated to solve on classical machines. So with this, I hope I gave you a lot of inspiration, and what I really want you to take away from this talk today is quantum computers are there, they're available, the hardware is there, it's addressable via cloud interfaces. You can sit down and program on it. They're really highly efficient for hard problems. They have intrinsic properties that make them very, very suitable for machine learning, and the impact that we will see in the upcoming years of this kind of technology across all industries will be huge. So, in my opinion, I think now is the time to start to think about quantum and how to apply it in a meaningful way. And I hope that this message came through. And if you have any other questions, feel happy to talk to me, or feel free to talk to me. I will be happy and delighted to go more into detail about this very, very interesting field. And with this, thanks for your attention.